Hello, this is Mike. This is Actuarial Modeling, video number 3. So today I'd like to cover a little continuation of the maximum likelihood estimator, and I'll introduce delta method, and finally a really fantastic example of using Mathematica to solve likelihood ratio test and chi-square statistic in no time at all. So we'll start with the MLE estimator. We already covered what it means, and easier example we already did. So this particular problem, we're given the survival function, as you can see here, of Sx. Relationship of the survival function and the density is the density equals to the negative first derivative of the density, known from the probability course. And we're giving 3 values, 2, 4, and another exceed 4. So you're knowing that the likelihood function, log likelihood, would be the logarithm of f2, f4, and s4. So knowing this, so first we're going to calculate the density from the survival function, which is the first line here, with full simplify. We hit shift enter, and that is the density. So using this density, I define this function fx. So I'm going to plug in the density and the survival function into the log likelihood, and which yields this. So finally we're going to use the nsolve command to set the first derivative with respect to this parameter theta equals to 0. I put a quiet here because if I don't, Mathematica usually will give me a nasty warning saying that well, in this case it didn't, but sometimes if you're solving the inverse exponentially, it will give you a warning that an effort has been made in order to find the root of this equation. So I personally prefer to use quiet. So it will just give you the number. So we are looking for the real theta. The first seems to be the answer, which is 5.65. So now moving on to delta method. Essentially is a great way to estimate the variance if you after a transformation of a probability distribution. So in this case we have a interval which is the symmetrical linear 95% confidence interval of the hazard function h5. And we're asked to use the delta method to estimate the symmetrical linear 95% confidence interval of S5. Now first is we have to know the relationship between the hazard rate and the survival function. In fact, survival function is equals to the e to the power of minus h. In this case, it's a capital H. If it's a lowercase h, you need a further integration. But again, we assume that to be the knowledge that you already have. Otherwise, this problem is really not quite doable at this point for you. But regardless, so having this interval, knowing that it's 95%, we can very quickly back out the mean and the standard deviation. It's not too hard. The mean is really the middle point, and the standard deviation is really the length of the interval divided by 2 times 1.96, which is the inverse normal distribution of the z-score with 0.95. So having these, we have the mean, which is 0.775, and the standard deviation. So we take the square in order to get the variance. So here is the variance of h. Okay, knowing these, we are going to use the delta method. So first we need to estimate the mean of the survival function, which is relatively straightforward, is merely the e to the power of minus h. So here is the mean of the survival function at 0.5. Now, the delta method comes in when we need to estimate the variance of S5. And here, this function coming from the 2 parts. First is you need to take the square of the first derivative. Now, fortunately, this transformation is merely exponentiation, so it's just e to the power of negative h with a negative, but that sign, because it's taking the square, it really doesn't matter. And that times 0.063, which is the variance of h that we evaluated earlier, which is right here. So knowing these, we got the mean and variance of survival function, and finally is really constructing the confidence interval is extremely trivial. Okay, and finally moving on to the third part of this really compact video is the likelihood ratio test and the chi-square statistic. So we're looking at this problem which is actually has a very straightforward purpose. We have a Weibull distribution and a random sample from it, and we're going to estimate the two parameters. We all know that Weibull distribution has two parameters, theta and tau, and there's absolutely no need for you to memorize the density function, as you can look up, but I'm reproduced here for convenience. This is the density when tau equals to 2, because we are already given, when you're trying to maximize the likelihood, the theta and tau, we have this sigma log of fxi equals to minus 33.05, and this is exactly the definition of the likelihood function, log likelihood of the model B, where you are going to estimate the two parameters. Recall that what is likelihood ratio test is the 2 times the difference between the log likelihood of a model with 2 parameter estimation and the log likelihood of 1 parameter estimation. So this is definitely the log likelihood of model B, so LB in the formula. And if we set tau to be 2, we're only going to estimate theta, and we're told the likelihood estimate of theta is 8/16/7. In fact, this information is not absolutely necessary, as we can actually prove that to be the case. So I'm going to show you that this has to be 8/16.7. As you can see here, we have the log likelihood given tau equals to 2 and set it to be 0. Now we are going to find theta, and that gives you positive and negative 8/16.7, and as theta has to be positive in a Weibull distribution, so theta is 8/17. So that's really redundant, but because it's a paper-based exam, so it doesn't really anticipate you to do a lot of very hardcore calculation. So knowing these, we are going to set theta into the equation to back out the log likelihood of the model A, where we're going to only to estimate one parameter, namely theta, which is given. So, and that comes out to be negative 35.2. So everything is complete. We're given the log likelihood of the model B. We're going to log likelihood of model A. We took their difference. Notice minus is a positive, so it's positive plus 35.28, which is the log likelihood of the model A, where only theta is going to be estimated, and times 2 gives 446. So we have the statistic. We go ahead and do the chi-square. You can look up the chi-square table, but a much more convenient way is to use Mathematica built-in wonderful CDF of chi-square distribution function. Here 1 stands for 1 degree of freedom. The reason being that one model we estimate the 2 parameters, the other we estimate 1, so the degree of freedom has to be 1. And we set the chi-square to be 9.95, the critical value is 3.84. So your statistic 4.46 is greater than that number, so that null hypothesis is being rejected, meaning that it is significant. But let's take a look at the 0.025 level of significance, and that critical value is 5, which is, our statistic is not there yet, so it's insignificant, so we can't reject at the 0.025 level. And so this, if we take a second back at this problem, we utilized some really great features of Mathematica 8 to solve this great problem. First is this ability for us to find our own function, and its ability to manipulate arithmetic expressions, simplify, and its ability to solve numerically functions, rather complex functions, including transcendental functions such as logarithm and exponentiation, and its ability to have built-in probability functions of chi-square, for example. So putting all these together, we're able to come up with a very meaningful answer for this really complex problem.